Good evening, everyone. My name is Benham Shadek, and I'll be taking you through gravitation mechanisms together with my colleague Katunja Brendan. So, a brief review we can take a brief review of the concept of graph neural networks, or GNNs in simple terms. So, a graph consists of nodes which represent entities and edges which define relationships between these entities. And relational neural networks, like convolutional neural networks, work well with grid-like data, but real-world data is often structured as graphs. Now, GNNs help process this complex data by learning from node and edge relationships. However, GNNs have some key limitations, like they treat all neighboring nodes with equal importance, which can reduce accuracy. And the second one is they use fixed aggregation methods which do not adapt to different structures. And due to these limitations, they led to the introduction of gravitation mechanisms, as we are going to talk about them in the next slide. Now, the core idea of gravitation mechanisms is to improve how nodes interact with their neighbors. Instead of treating all neighbors equally, attention mechanisms, they assign weights based on the importance, and this ensures that the node prioritizes more relevant information while filtering out the less useful data. We can think of this like more of a social networks. Now, if you're trying to make a decision and you have opinions of close friends and those which are maybe distant friends, so you choose the opinions of the friends who are above. Now, similarly, the gravitation mechanisms, they allow nodes to focus on more influential neighbors while reducing the impact of less relevant ones. Now, let us talk about how the gravitation network works. Now, the first step is input representation, where each node in a graph has a feature vector that represents its attributes, and these features are then transformed using a weight matrix W. Now we are talking about the linear transformation, and this transformation allows the network to learn more meaningful representations of the input data. You can think of this as converting raw data into a format that is easier to analyze and compare across nodes. And the next steps we can talk about the computation of attention scores. Now, after transforming the feature vectors, the next step is to compute attention scores, where each node evaluates its neighbors and assigns an importance score using an attention mechanism. And this can be mathematically represented using this formula below. Now, here, this one is the attention score between the nodes I and M, and W is the learnable weight matrix, and this one AT represents the attention vector, and these two, how do I call it? These ones they represent concatenation. Then we can talk now. Let me talk more about the computing attention scores. Now, from there, we go to the normalization of the attention scores. Now, to ensure these scores are meaningful, we normalize them using the softmax function, ensuring that they sum up to 1 across all neighbors. And this is crucial because it helps to determine how much influence each neighbor should have in the final output. And the practical analogy would be a voting system. Now, if multiple sources give you information, you weigh their options based on the credibility before making a decision. And that is what the normalization is all about. And that's why we use the softmax function. And we use this formula, which is here below. And finally, the last step is aggregation. Now, once attention scores are assigned, the final step will be aggregation, as I said. And now each node updates its feature vector by computing a weighted sum of its neighbors' features, and this means that more important neighbors contribute more to the final node representations, and they're represented using the formula below, which is this one, and where this one hi prime is the updated node representations, and this symbol here, sigma, represents nonlinearity. And so that's basically how the graph attention networks work. So the first one is input representation. Excuse me. Well, we understand that each node in the graph has a feature vector. Then linear transformation, where we transform all the input features. Then the next step will be computation of attention scores, where each node examines its neighbors and decides how much attention to give it. So in brief, we are measuring the weight of the node is measuring the weight of its neighbors. Yes. Then the next one, we are going to normalization of attention scores, where I use the softmax function to ensure that all the scores sum up to 1. Then the last one will be the aggregation. Now, the other thing I can talk about is we want to compare the traditional machine learning models versus the attention mechanisms. And CNNs and RNNs, they work well for the structured data like images or sequences, but they struggle with graph data, where the relationships between nodes matter just as much as the nodes themselves. Now, the graph attention networks, they were introduced to improve upon the traditional machine learning models like the CNNs and RNNs, as we have talked about, by using attention mechanisms to assign adaptive weights, then learning more meaningful representations of graph structured data. And this makes graph attention mechanism particularly useful for applications where relationships and interactions matter, such as social media analysis, fraud detection, and the drug discovery, as we shall talk about them in one or two of the next slides. Then now we can talk about the challenges of using the graph attention networks. And the first one, you have high computation cost. Now, the attention mechanisms, they require matrix multiplications for every edge, and this would increase the computation cost of using the graph attention networks. And then the second one is memory usage, where storing the attention weights for large graphs can be a challenge. Because for each node, for the node and other nodes, it will always calculate the weight, or the weight, because it's basing on this weight, it's going to like assign the importance. How important is this node, this neighboring node to me as a node? So after calculating all those, it will be challenging, because there will be very many nodes, because if a node is surrounded by let's say like 50 other neighboring nodes, so storing all that, and remember it's not only one node, so storing all that can be a challenge. Then you can talk about overfitting on small data sets, where multi-head attention can introduce too many parameters, and long-range dependencies, where graph attention networks struggle to model the very deep graphs effectively. And lastly, let me talk about the real-world applications. Now, the first one I can talk about is fraud detection. Now, Financial fraud is a major concern, especially in the banking sector and maybe online transactions. And now, graph attention mechanisms help to detect any fraudulent activities by analyzing the transaction networks. They identify the patterns where fraudulent transactions cluster together, making it easier to detect suspicious behavior. Yes, let us continue where we stopped. Now, I was talking about we are talking about the real world applications of the graph attention networks or graph attention mechanism. Now, the first one would be fraud detection, where the financial fraud is a major concern, especially in the banking sector and these online transactions that take place maybe on the web. Let's say we are making a transaction on Jumia, you're buying a commodity on Jumia. So those are the online transactions we're talking about. Now, the graph attention networks helps to detect fraudulent activities by analyzing transaction networks, and they identify patterns where fraudulent transactions cluster together, making it easier to detect any suspicious behavior. So they're going to cluster any fraudulent transactions which they may detect, and this makes it easier to detect any maybe behavior that is suspicious. In case they detect that this transaction is not legal or ethical, they detect it and they stop it immediately. And unlike traditional rule-based systems, the graph attention networks can dynamically adapt to new fraud techniques. Now, as we know that these scammers keep on coming up with new techniques of stealing money from people's accounts. So the graph attention networks, they can adapt to any new fraud techniques that have been brought up by these scammers. Yes, by these scammers. And so the next one we can talk about social media analysis. Now, in social media, misinformation and fake accounts pose serious challenges, and graph attention networks are used to analyze the relationships between accounts, identifying bots, fake news spreaders, and malicious actors. And you have noted this on various platforms which you use, like Twitter, which is now X, and Facebook, where you may find there are people who generally opened up accounts to spread fake information. And lately we have seen they have introduced some systems that are able to detect any fake information, and immediately they detect that the information is not true, it's not coming from a legal source, they immediately declare it fake. Excuse me. Now, by assigning the attention weights to different interactions, they can distinguish between genuine users and automated accounts, those ones which are spreading any misinformation. Next, we can talk about drug discovery. Now, pharmaceutical companies also use the graph attention networks to predict molecular interactions. Now, in drug discovery, the molecules can be represented as graphs where atoms are nodes and chemical bonds are edges. And by applying graph attention mechanisms, researchers can predict how molecules they interact in biological systems and accelerating the process of developing new drugs. So this will help them to develop. So if they see using the graphs, because remember, when we have graph structured data, it can help us to easily analyze how is this drug performing, how is this drug maybe affecting this and this. So it can help them to develop new drugs which are brought on market to help the people. And second last, I can talk about the recommender systems, where platforms like Netflix, Amazon, YouTube, Spotify, they use recommender systems to personalize user experience. Now, graph attention networks were introduced to enhance these systems by analyzing user item interactions as a graph and prioritizing relevant connections, and this helps to improve recommendations, ensuring that users receive suggestions that best match their preferences. You can see this mainly on, I can take an example of YouTube. Remember, YouTube, once we keep on searching for particular things on YouTube or watching particular videos, the 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 algorithm the algorithm keeps on understanding what kind of content should appear on this person's home. So that's why when you open your YouTube, the stuff that you mainly the, the stuff that you mainly search about the ones which appear on your home, so that you easily access them. So that's the same to platforms like Netflix. Next, we can talk about the autonomous systems, where the self-driving cars and robotics mainly rely on gravitational networks for efficient decision making. And we know the self-driving cars that have been invented, like the Tesla. We see like the automated taxis that are operating in China. So they do all this by analyzing they do all this by analyzing the road networks, the traffic signals, and the interactions between moving objects. And gravitational networks, they help autonomous systems make safer and smarter navigation decisions, and this ensures adaptability in complex environments. Let's say that it is driving on a highway where there is high traffic. So it is using gravitational networks and what we have just talked about, through analyzing the road networks, the traffic signals, and the interactions between moving objects. So it will have adapted to this complex environment. So that's it from me. Let me allow my colleague to take you through the next part. Thank you.
Good afternoon. I'm Katunja Brendan. I'm in Group 22, Machine Learning, Computer Science Year 2. I'm going to talk about the implementation of the machine learning graph attention mechanisms. Talk about the implementation. I mean about the code and how it works in different features. For example, the self attention, the soft normalization, aggression, mentioned by a few. So we are going to start with the self-attention mechanism. Here, each node computes the attention scores for its neighbors. Instead of simply averaging, attention weights are used to decide how much information to take from each neighbor. Talk about the code. This code uses a self-attention mechanism where each node learns how much attention to pay to its neighbors. Also implemented as the pie chart as the PyTorch module. It has two layers. It has the first layer, which is the conv1, and then the conv2. The conv1 layer takes the input features and then transforms them using the 8 attention heads, and then the second layer it combines the features from all the heads into the final output. It also includes the dropout, which is 0.6 for regularization, prevent the overfitting. To move on to the second slide of the implementation, we shall talk about the computing attention scores. Here, for each node, J1, Ji, we compute the attention scores with its neighbors, J, a transformation J, and then a small neural network, typically a feed forward layer. It computes these scores, and then these scores determine how much weight each neighbor has. So to talk about the code, talk about this code. These attention scores determine the importance of each neighboring node's features, and also the process happens in each attention head independently, and the head's parameter determines how many different ways the attention is computed. So here it is basically 8 heads. For our case, we used our data set, and then we came up with a graph to make this implementation of the code. So we are going to move on to the next, which is normalization. Normalization, after computing the attention scores, we normalize them using the softmax. This ensures that the scores sum up to 1 across all neighbors. This happens inside the getConf function internally, and this ensures that the computed attention weights are normalized properly. So this code here, attention score is equal to f softmax in brackets raw attention scores into dim1. This one happens internally in this function of getConf. So we are not able to actually see how it works, but this is the raw format if it is going to be implemented manually. So let's talk about this softmax normalization. The raw attention scores are passed through the softmax function, and then the dim1 parameter means that the normalization happens across the neighbor dimension, and this ensures that the attention scores for the node's neighbors sum up to 1, and then normalization happens internally, as I have said. And then this step is very crucial during the creating of the proper probability distribution over the neighbors. So we are going to move on to the aggregation. Here each node aggregates messages from its neighbors using the computed attention weights, and also it allows the selected it allows it to selectively focus on the important neighbors while ignoring the relevant ones. So talk about this code snippet. The forward method takes the node features x and the graph structure edge index as I as the input, and also the conf1 layer here, which is right here, which is the self.conf1, performs the convolution, and then the operation that aggregates the information from the neighboring nodes, and then the aggregation is weighted by the attention scores computed for each neighboring following the node to focus on the important neighbors while giving less weight the relevant ones. So we are going to move on to the next implementation, which is the multi-head attention. Here, instead of one attention mechanism, multiple heads are used, and then these heads work independently and are later combined for better feature extraction. The head is equal to heads argument is set 8, as I had said earlier, the previous implementations. So this code snippet, when we talk about this code snippet, it uses the getGov function, which involves the graph attention convolution layers, and the first layer conv1 uses the multiple attention heads, which is set 8, and also for each head learns from different aspects of the relationships between the nodes. And then the second layer also, which is conv2, combines the outputs from all the heads, and also this dropout 0.6 helped prevent the overfitting, and also talk about the hidden channels. Shows how the features from all the heads are concatenated. So we are going to move on to another implementation to talk about how important this conv function is that it does everything for us internally, and then instead of manually implementing the attention scores, softmax, aggregation, PyTorch metric, geometrics, getGov handles them automatically. So the only thing that we specify is the number of heads, which is 8, and then the dropout, which prevents the overfitting. So I'm going to combine these different code snippets to come up with a full implementation combining all of them. Here we are. So start with, we first import the important libraries. The one of Torch is the core Torch library, and then the Torch.function provides the functions like activation functions, and loss functions. And then the touch geometric, it imports the graph attention network, convolution layers, as we were using them in the, for example, the soft normalization, and also the talk about the touch geometric data. It is used to store the graph related data. So we are going to move on to the first line of our code after importing the necessary libraries. This touch device function, it is used for checking the GPU if it is available. For example, me, I was using the Kotlab, so we were provided with a free GPU. So if it's not available, we use the CPU, which uses a lot of resources when you are using the local machine. And also we are going to move on to the graph data. It moves the graph data to the device, either the CPU or the GPU, and then this class GAT, it creates the graph attention network module, and also the init method, it initializes the channels number. It initializes the number of channels, the number of input features. In this case, we have, after we have talked about the different implementations, say as the self-attention, the soft normalization, and then the aggregation, we are going to combine these different features to make one complete code. So to start with, we are going to start by combining the libraries. By importing the libraries, we are going to need the touch. It is the core touch library we are going to use, and also the touch end function provides the functions like activation functions and the loss function. The geometric input imports the graph network attention for the convolution layer, and then the geometric data input is used to store the graph related data. So we shall move on to the touch device. This one checks if the GPU is available. If yes, it uses the GPU. For example, we use the Colab, so we use the Colab, we use the GPU. If not, it uses the CPU. This one requires a lot of resources. And then we shall move on to the graph data. It moves the graph data to the device, either GPU or CPU, depending on what you are using. So we shall move on to the class GAT. It creates the graph attention network module, and also it initializes the channel. Initializes the in channel, where we have the number of input features per node, and also the hidden channels, the number of hidden units per node, and also the number of output classes. Finally, initializes the attention heads in the first layer. So we shall move on to the function forward. This one defines how data moves through the module, and also passes the node features. Applies the ELU activation function to introduce the non-linearly, and also passes the updated features to the second GAT layer. So shall move on to the next module, which is the GAT in channel. This one, it creates the instance. It creates the instance of the it creates the instance of the GAT module, and then it specifies the 7 input features per node, and also the 8 hidden units, and then the 2 output classes, and then it moves the module GPU or the CPU, depending on what you are using. And then also we shall move on to the touch optimizer. This one, adjusts the model parameters to minimize the loss. For example, here we have the learning parameter as 0.005, and then the learning rate, which is the step size, and then the weight decay, which is 5e, and then 4, and then regularization to prevent the overfitting, as we already said in the individual implementations. So we shall move on to the train mask. The touch rad. This one randomly selects the 70% of the models of the nodes for training, and the rest, which is 30, and is used for testing. So shall go on to the data chain mask, which this one moves the mask and then the test mask to GPU if available, or CPU depending on what we are actually using. And then the function train, this one sets the model to the training model and also clears the old gradients. It performs the forward pass and also calculates the loss using the only training models, computes the gradients, which is the loss backward, and then updates the model parameters depending on the optimizer step, and then returns the loss value. Thank you.